Davis, and I'm a graduate student at Cornell University. I'm part of the new Carl Sagan Institute. It's very exciting. I'm going to talk about it more. And, oh, I don't get a timer like everyone else? Okay, cool. So I'm going to be talking to you guys about UV environments of Earth-like planets orbiting white dwarfs. So the warm-up talk was really good. Thank you for that. I'm going to still review some of it in case you weren't listening, or, it's just fun. All right, so my main motivation and the main motivation of our group is to look for life in the universe. And we have no idea what kinds of forms that life can take, but we know that we're life. So we're going to start with that and then maybe branch out from there. So that means I care about habitable zones, I care about where liquid water could be on the surface of a planet, and I care about possible biosignatures. And one of the big goals of the Carl Sagan Institute is to sort of build up this kind of spectral library for future reference. So in the future, when we can actually spectrally characterize exoplanet atmospheres, maybe we'll know what a desert world would look like, or a water world, or an Earth-like planet orbiting a white dwarf. What? Okay. So, is there a laser on this? Ah, yes. Okay, so this was covered briefly in the warm-up talk. Thank you for that. So, most of a star's lifetime is when it's on the main sequence. Simply put, that's just when in the core of the star, it's fusing hydrogen. So we're right here. Most of the star's lifetime is the main sequence. So the main sequence is what's mainly been studied, and it's great. My whole thesis is everything but the main sequence. So I'm going to be looking at white dwarfs, tiny but fierce. It's very exciting. So why do we care about planets around white dwarfs? You might be thinking, I've never heard of a planet around a white dwarf. That's because none have been found yet. But there's a lot of evidence for it, which is why it's very exciting. And so there is a disk picture in this talk, too. So the majority of white dwarfs show evidence of recent accretion of rocky bodies in their atmospheres, which there have even been some papers that are able to reconstruct exactly what would have had to fall on the white dwarf to create that pollution. So it looks like most white dwarfs have rocky bodies accreted on them. So maybe not all of the planets fallen on them. Also, it would be people believe it would be very easy to detect in a transit. So like mentioned before, a white dwarf is about the size of Earth. So if we're using the transit method, so we're looking at the white dwarf, waiting for something to dim its brightness, if Earth passes in front of it, it's going to block all of the light, and that's a really strong signal. So there's actually a bunch of studies going on looking for these white dwarf planets. In particular, K2 is really excited about it. So what I care about, though, because I'm me, is if these white dwarfs do have planets, under the best conditions, are they suitable hosts for life? Or will the UV just irradiate them? And if there is life there, would we be able to detect it? So the atmospheric composition of these planets and taking into account how they would interact with the UV profile of the white dwarf will help us answer these questions. So as I'm sure a bunch of you know, atmospheres of planets are affected by so many things. So I'm going to pay attention to two of them. This is what I'm going to pay attention to. I'm going to look at the photochemistry, which if you're a physicist like me and that word scares you, it's just UV photons. They're really high energy. They're just going and they're breaking apart molecules and they're changing the chemistry of the atmosphere. And then I care about three different types of UV, which are pictured here. So UVC is most dangerous, UVA is not. So UVA is actually pretty useful. It helps power complex processes. UVB, if you've ever had sunburn or a tan, it's UVB's fault. It's partially shielded by ozone. And then UVC is a lot worse than sunburn. It destroys your DNA. So that's what I care about the most here. And it's almost completely shielded by Earth's ozone layer. So for the sake of this short talk, I'm going to mainly talk about this potential biosignature, even though there are multiples, and hopefully we'll hear more about them later. Originally, people thought if we're looking for indications of life in the spectrum of an exoplanet atmosphere, maybe we just have to look for oxygen. You're like, oxygen, that's life. But we later on realized that oxygen can be created by non-biological sources. So we want to know if it's biological or just something else, because we care about the biology. So we want to see basically oxygen with something that's destroying the oxygen. So we know the oxygen is being continuously created by life. So methane is the example I'm going to use here. It is a reducing species. It's created by termites, natural gas, all of these things that life does. And the main chemical processes, reactions of methane destroy oxygen. So if you see strong oxygen signal and then also methane, we have a pretty good idea that the oxygen is being continuously produced. Some people argue with this. You could come talk to me about it afterwards. Okay, so really briefly, just so that everyone knows what I'm going to be caring about in this talk, I care a lot about the ozone layer, because like I said before, that's going to shield the UV and protect surface life. So the ozone is created by shorter wavelengths in the UV. So we care about that because of UV shielding. And also important is that ozone photolysis also creates hydroxyl, OH, and we care about that because it's called the detergent of the atmosphere, which basically means it reacts with a bunch of other species that we care about and it depletes them. So it does fundamentally change the atmosphere. Like I mentioned before, I'm going to talk mainly about methane. If you want to hear about all the other species that I care about, you could come talk to me after, or you can read my paper. You could get lots of reads on ADS. Great. So yes, lots of methane being destroyed by hydroxyl. Okay, so like I mentioned before, most people have looked at the main sequence. And I'm looking at white dwarfs. So what do I need to take into account about a white dwarf? The spectra are different. So there was something like this in the warm-up slide. If you'll notice here, so I have the three temperatures. I have 6,000, 5,000, 4,000. The red lines are from main sequence stars, and the blue ones are from white dwarfs. And you'll notice that these the white dwarf sort of looks like a black body. That's because white dwarfs are highly differentiated because there's no fusion going on. So the heavy elements sink to the center. So if you're looking at it, you're basically just seeing only hydrogen lines, and 5,000 Kelvin and under, hydrogen is neutral, so you don't even have those lines. What I really care about is the UV. So like I mentioned before, there's the three types of UV, which I have color-coded here in fun traffic light colors for you. And you'll notice here the blue lines are the white dwarf, the red main sequence for the same temperature. So you can see that there are definitely differences here. And also all of these are scaled to the solar constant. So they're all scaled to the 1 AU equivalent to yield roughly similar surface temperatures. So one of the main differences you see here is that there's a little extra UV for the main sequence there. That's due to chromospheric activity, so just what's going on in the atmosphere of the star. So just looking at all of these from the first time I looked at it, 4,000 Kelvin case is most different. So I was thinking the photochemistry would be most different there. Let's see. Okay, so the models that I ran, I basically put in planets that were the same as Earth with the same outgassing rates of life. And I ran the three temperature cases for white dwarfs and the main sequence stars. So why did I pick those temperatures? There was actually a reason. As Sunny mentioned during the warm-up talk, the white dwarf is cooling over time. So it starts off very, very hot and cools over time. And the habitable zone is continuously changing. So we want to look at a time when the habitable zone stays in the same place for long enough that life can grow and evolve. So if you look between 6,000 and 4,000 Kelvin, that's about 10 billion years right there. And considering that we are much less than 10 billion years here on Earth, I'd say that's enough time. So that is why I picked those. I didn't pick anything less than 4,000 because white dwarfs that cool don't really exist yet because the universe isn't old enough. So I try to be a little realistic. Speaking of realistic, here's the 1D climate code we use. It's a coupled climate photochemistry code. Basically, it calculates the temperature pressure profile looking at the major greenhouse gases. Then it goes into the photochemistry code, And it uses the temperature profile to update the chemistry. You update the chemistry, then you update the temperature, then you update the chemistry, and you just sort of go back and forth until it's reached equilibrium. And you have the star as an input. So you get the atmosphere to reach equilibrium for that specific star. For the results, I know that different people learn differently, so I have a graph, and then on the next slide, I also have it in words if you hate graphs. So here, really quick, just hitting on the highlights. We have each row is a different temperature. Just at first glance, you can see the 4,000 Kelvin case is the most different, as we all predicted together. So there's actually an excess of ozone a little bit in each case, which actually caused more hydroxyl to be created, and that caused more depletion of methane. So there was more ozone because there's more UV at specific wavelengths, which caused more hydroxyl, which caused less methane. And then I put in water, because we all care about water. And you'll see there is a difference, mainly in the 4,000 Kelvin case, because at the wavelengths that water is broken apart by photolysis, there was a lot more of UV flux at that wavelength for the white dwarf than the main sequence star. So in words, basically, a lot of the white dwarf planets, compared to the main sequence star, at the wavelengths where ozone is created, there was more ozone, which created more hydroxyl, and the hydroxyl depleted the methane. And also, I didn't talk about these, but I put them in for fun. Because of the increased hydroxyl, there was more CO2, which is a very potent greenhouse gas, and then more methyl chloride and nitrous oxide, which are other biological species. And real quick, here's an idea of what the UV to the ground looks like. For reference, we are roughly like this 6,000 Kelvin main sequence star right here. You might notice that ozone is most efficient at shielding at around 260 nanometers, which is why they're that shape. So you could see that the stars with less UV flux, the cooler ones, are actually, they have more UV at the surface, harmful UV, and that's because there's less ozone. So this is more just a general comment for stars, but if you're going to compare white dwarf planets to main sequence planets, the UV to the ground is comparable, so we don't have to worry about surface life being irradiated. So in summary, we have to really, with white dwarfs, think about the changing habitable zone. As the white dwarf cools, the lack of chromospheric activity causes changes in the photochemistry. The UVC shielding is comparable, so we don't have to worry about DNA damage. And also, with the hydroxyl, there could be depletion of potential biosignatures for the white dwarfs. So even if there is life there, it might be more difficult to find it. So the paper I'm writing right now is creating planetary spectra for these models. So I will be doing an analysis of the biosignature detections. So thank you.
Hi, that was a really neat talk.
Thank you.
So I have a quick question regarding the white dwarfs and proposing that you would have a habitable planet. What's a scenario you can envision in terms of having the raw material, hydrated material that would be able to survive the transition to a white dwarf through the red giant expansion phase?
That's a very good question. My advisor says officially I'm not supposed to comment on this, but because we just care about the modeling. But as I mentioned earlier, that there are a lot of disks that sort of resemble protoplanetary disks found around white dwarfs. So there could be some sort of second wave planet formation with then late water delivery.
Thank you.
Thank you.
That was an absolutely fantastic talk.
Oh, thank you.
So my question is, and maybe this is embedded somewhere in the modeling, but so you mentioned that obviously the habitable zone is highly dependent on the rate of cooling. You also mentioned that due to these photochemical effects, you're getting a lot of carbon dioxide, which, as you mentioned, is a greenhouse gas.
Yeah.
Therefore, would that potentially be conducive to having a habitable temperature range on a planet for a longer period of time, just because you have all that CO2 to keep it warm even as the dwarf cools?
Yeah, oh, that's very interesting. Yes, it possibly could. Yes, thank you. Totally possible.
Okay.
Be my co-author, we'll do it together. Yes.
I might have missed this, but how did you decide what your atmospheric composition was, and is it just like starting with like the modern Earth atmospheric composition, or?
Yes, I'm actually also writing a paper on Earth throughout time around white dwarfs. I'm just really into white dwarfs. Yes, we were using modern Earth for this as sort of the best case scenario and seeing if we could even detect life and have life exist starting off from Earth.
Okay.
Just very stupid question.
I'm sure it's not.
What's going to happen to white dwarfs at the end of their lives? Can they become a planet themselves?
So white dwarfs, when they cool down completely, they become black dwarfs. But those don't exist yet because the universe isn't old enough. So it just sort of cools down completely, and then it's just there, being really dense and very cold, and it's very sad. But don't worry, they don't exist. Don't let that keep you up at night.
Since you're messing with the atmospheric chemistry, do you know what's going to happen to cloud formation and aerosol formation? Because that really affects the temperature and the biosignature detection.
So I'll put in a plug for my office mate, Jack Madden's poster, which is eventually this week, where he will talk about those sorts of effects. So yes, these were clear sky models that I used. Our code does use clouds, but this was just sort of to see, even with everything going perfectly, could we still detect life? But yes, clouds have a big effect. So Jack will explain that later.
Hi, I might have
Yeah.
missed this, but how different is the radiation environment around white dwarfs than like M dwarfs, which also have high UV?
Yeah, so the white dwarfs don't have flares like the M dwarfs. The main difference between the UV, as I showed before, is that the white dwarfs don't have chromospheric activity, which white dwarfs literally look like black bodies. Whereas if you have a main sequence star with chromospheric activity, there's a black body, but there's also a bit at the end tacked on from the chromospheric activity. So it's just mainly that.
Thanks.
No problem. Should I?
One last quick question.
All right. I'll be super fast. Have you thought about maybe doing some sort of bench work, looking at polymerization under different UV radiation environments? For example, if you have a more lean starting chemistry for a white dwarf scenario?
I haven't, but that's a good idea. I'm open to lots of different things. I have like 30 years of grad school left, I figure, so I'm going to do it all.
And on that high note, let's thank Thea again.
Thank you.